Oh my God, it worked. Okay, right. Sorry for the delay. Hello again, maths fans. Yes, thank you, Eric. It just froze on my face. So sorry about that. You just had 2 minutes of my frozen face, but I think we are now up and running. If you can't hear me or see me or something else goes horribly wrong, please do let me know in the chat. So, hello everybody. This is the fifth even, isn't it? God, these things are flying by. This is the fifth Tom Rocks Maths Appeal live stream. So I've been doing these as part of the Tom Rocks Maths Appeal series, which we've been running over the last few weeks with my friends Bobby and Susan from Maths Appeal. Hello, Bobby and Susan, if they're watching. So the theme this week in our video lesson was trigonometry. We actually got more questions sent in on this topic than any other, which I think tells you something. Either people really don't know what they're doing with it and have lots of questions, or people really enjoy trigonometry and therefore have lots of interesting questions. So either way, I've got lots and lots of questions that I'm going to try and get through in the first sort of, let's say 40 minutes or so of the live stream. And then, as I've done before, I'll open up the last 20 minutes to any questions at all, anything to do with maths in the live chat, and I'll see if we can get through some of those. So to kick us off, we have a great question which has come in from MJ. So hello, MJ, if you're watching. Thank you for the question. And MJ asked about something called the things called the sine and cosine laws. So I'm going to kick off by talking about the sine and cosine laws. So we're going to start with a triangle. Let's draw myself a triangle. You'll notice this is not a right-angled triangle. This can be any triangle. And then I'm going to label my unknown angles A, B, and C. So I've just got any old triangle, 3 angles. And then we label the opposite side to the angle with the same letter. So this has length, side length A. This is going to be side length C. And this is side length B. Now, the sine law tells us, that A divided by sine A is equal to B divided by sine B is equal to C divided by sine C. So this is saying if you take the length of one side of your triangle, this can, remember, can be any triangle, doesn't have to be right-angled. Just take the length of the side and divide it by sine of the angle opposite that side, then these 3 things will be equal. Now, the more interesting question is, where does this come from? So that's what we're going to look at. And the way to do that is to use trigonometry, right? So there's kind of a clue. It's called the sine law, because we're talking about cos and sine, and we're talking about trigonometry. So if we add a straight line down from this top angle, then this, on both sides in fact, is now a right angle. And so if I call this side, this middle thing, X, let's call it, then what we have is a right-angled triangle, and I'll draw it out, let's say down here a bit clearer. So I've got side length X, this one's C. This one I don't know, but I do know this angle A. So I don't know the angle at the top. I don't necessarily know the length here, because this could be any triangle, remember. But I definitely do know this is angle A and this is side length C. So I've got an angle and a hypotenuse, and I'm interested in the opposite side, X. I want to find X. So I've got hypotenuse, opposite, SOHCAHTOA, silly old Harry, however you remember this. If anyone else has any good ways of remembering the trigonometry rules, please do share them. I've seen quite a few in the YouTube comments, and they've been very entertaining to read. So I would go with silly old Harry caught a herring traveling over America. So silly old Harry means sine of A is equal to opposite over hypotenuse. Opposite is X over hypotenuse is C. So this tells me, from my rule of trigonometry, that X is equal to c times sine of a. Right, so now I know the height of the center of my triangle. Now I know the height of my triangle. Now, we want to try and do this for the other half, the other side of the triangle. So I've done this using angle A, so I can flip it and do it for the other half of the triangle here. So I've got C, I've got X, and I've got A. This one now. So again, if I apply my, it's going to be sine again, because I'm interested, I've got the hypotenuse, I'm interested in the opposite. So silly old Harry is going to tell me that sine of C is equal to the opposite x over the hypotenuse A. And so that's going to give me that x is equal to A sine of C. So we have two equations for x, and they both have to be true, because they're both just based on our trigonometry rules. So if these two are equal to each other, because they're both x, then what that tells us is that C sine A is equal to A sine C. And so if I rearrange that, that's the same as, whoops, C over sine C equals A over sine A. So that gives me this one is equal to this one. So that's the first part of my sine rule. And then you could go back and do the same. So instead of drawing my line going through angle B, if I were to go back, get a different color. If I were to go back and do something like that as my line through angle A, then I could now create a similar formula involving B and get the same result, that this was also equal to B divided by sine B. So the sine rule, the sine law is this thing. A over sine A equals B over sine B equals C over sine C for this triangle. And we derive it, it follows by just doing the trigonometry rules SOHCAHTOA that we talked about in our video lesson. All right, and then the other one that MJ mentioned, I'm not going to do a derivation, but also MJ did ask about the cosine law. So the cosine law is same triangle, but now it tells me that c squared is a squared plus b squared. Now it isn't a right angled triangle, so Pythagoras doesn't apply. So we have an extra term here, which is minus 2ab cos of c. So the first part is like Pythagoras' theorem, but remember, we don't expect Pythagoras to work because the triangle ABC is not a right angled triangle. So the cosine law just tells you how to work out your side length C, let's say, in terms of the others, if it's not a right angled triangle. And you can derive this formula in the same way as I worked out the sine law. You draw your sort of perpendicular lines and you use trigonometry, SOHCAHTOA, to work out various different relationships, and you can rearrange to get this. But that one takes a lot longer, so I think I've probably done enough just going through the sine one. So I hope that's okay, MJ. That's the sine law and the cosine law. Good question. Right, the next one, now this one's very fun. Big fan of this question. This one was from Sarah. Sarah, you sent a lot of questions in, so thank you again, Sarah, and hello. So this one, Sarah's question was, Sarah wanted to know about the functions sec, cosec, and cot. So can anyone tell me what is the relationship between sec, cosec, and cot to our normal trigonometric functions, sine, cos, and tan? I'll let you think about that. And if you want to type it in the chat, please do, whilst I clean the board. So sec, cosec, and cot. What on earth are they? Awesome. Georgie and Sam, thank you. Reciprocals, they are indeed. So we've got sec of x is 1 over cos. Let's do it up here. Cosec is 1 over, whoops, cosec of x. Let's do it properly. 1 over sine of x. And then we've got cot of x is going to be 1 over tan. Now, so this is the relationship. They are just reciprocals. So if you know the value of cos of an angle or sine of an angle or tan, then the value for sec, cosec, and cot is just 1 divided by that. So I think we did an example of cos of, which one was it? Cos of 60. Cos of 60, for example, is a half. And so if we were to plug in a half here, sec of 60 would be 2, for example. Now, the interesting thing about these functions, I think, is trying to draw the graphs. So let's have a go at that. So what I'm going to do is do 3 sets of axes for each of our graphs. Try and fit this all on the board. So first of all, Sarah, that's how we define these functions, and that's how you work out the angles. Like I said, just 1 over whatever cos and sine are, or tan. But now the graphs, I think, are more interesting. So that one, and then let's draw a 3rd axis here. Right, so our starting point is going to be first to draw the graphs of cos, sine, and tan. Because if we draw the original graphs, which we are more familiar with, then that will be helpful in trying to draw the reciprocal of the graph, right? Because it's just 1 over whatever value sine, cos, and tan have. So if we start with cos, so cos of 0 is 1, and then it comes down, and then it comes back up, right? So, and then it'll be the same over on this side as well, nice and symmetrical. Possibly the best cos graph I've ever drawn. Okay, so that's our cos function. It's meant to be symmetrical. Okay, it's not quite as good as I thought. It's almost symmetrical. Then we're going to draw our sine graph, which is the same but kind of shifted. So it kind of looks like that. And then this way, it's going to go up and then come down. Right, they're meant to be the same height. And then tan's a bit fiddly. But tan goes through 0 and then goes up to infinity. And then kind of does the same down there. And then for the next part, it looks the same as well. It comes in like that, where these are the same points. And if I'm going to draw this properly, I should also add in the last part as well. So then it's going to have to come in and go like that. Right. So as we can see, sine and cos are like the same thing. You take your cos and you just kind of shift it across by 90 degrees, and you get sine. It's basically what's happening there. But tan is very, very different. Tan has these sort of infinite points, or these undefined points, which we talked about in our video at 90 degrees and also at minus 90 as well. So if we want to now plot the inverse functions, that's what we're interested in, you can kind of just look at the graph and think about basically taking the value of the graph and flipping it. So for example, when we are at 1, when cos is 1, 1 over 1 is still 1. So we're going to be here for sec of 0. And then as cos starts to get smaller, we decrease away from 1, right? So say we get down to like, suppose that's a half. Then sec has actually increased to like 2, right? So as cos gets smaller, sec gets bigger. So what you've kind of got here is this thing like this. And what's going to happen when cos gets to 0, we've got 1 divided by 0, which is undefined or infinity. It's going to tend to infinity. As cos tends to 0, which is when x goes to 90, then sec will go to infinity. So you actually end up with a sort of U shape like this, going all the way up to infinity, like so. And then you're going to get the same thing down here, except it's now negative. So same idea, the cos values are now negative, So sec is 1 over a negative number. And it's, as we get to here, it's got to go to minus infinity. And then it touches, and then it comes down. So you just kind of take these bits and do that, and do that. And then there'd be another bit here as well. Another bit there as well. So the thing in pink, hopefully it looks pink to you guys, is going to be the sec graph, which is just 1 divided by the cos graph. So it's pretty funky. And then the sine function is going to be very, very similar, the cosec function, because as I said, cos is the same graph as sine, just shifted a little bit along the x-axis. And so what we can do is basically just shift our pink U-shapes to coincide with the bumps in the sine function. So you get exactly the same thing here, here, and then the negative ones down here. So sec and cosec are very much the similar graphs, just a shift, exactly like sine and cos are just a shift of each other. Now, cotex. So tan was already a pretty funky graph. We already had these bits going to infinity. So cotex, again, is just 1 over the value of tan. So that one's in purple. This is going to be in purple. So at 0, when tan is 0, 1 over 0, infinite. So as tan tends to 0, cot will tend to infinity. So here we're going to infinity. And then as tan gets bigger and bigger and bigger, 1 over it gets smaller and smaller and smaller. So while this one goes up and increases towards infinity at 90 degrees, cot decreases and has to go, when we have 1 over infinity, which, we should do this properly and take a limit, but let's just go with it. 1 over infinity is 0. You're dividing by a bigger and bigger number. 1 divided by something bigger and bigger and bigger is going to just drop down to be 0. So that goes through 0, and then it's going to then start to be negative and do that, as we had before. And then you're going to get the same thing over here. So let me just think about this. So this bit has to be negative, and then come in, and then as you go through there, like that, and then that bit's going to then grow up like that. So you end up with very, very similar cot and tan, but just kind of, you could think of it as like reflecting, in fact, in sort of a central axis. It's like one's a reflection of the other. So great question, Sarah, asking about cosec, sec, and cos. We can just define them as 1 over cos, sine, and tan, and then we can draw these pretty cool graphs. Right. Where did I want to go next? I wanted to stick talking about graphs. So we're not gonna we're gonna leave sec and cosec and cot for now, but we're gonna come back to cos and sine. And in particular, this is a question from Joe, who was interested in different graphs of sine, where instead of just plotting sine of x, you plot slightly more complicated functions. So, for example, sine of 2x, or sine of 3x, or even x times sine of x. So I'm going to look at a few of those graphs next. Here's the plan. And I see there's been a few questions posted in the chat. Again, I'll come back to them when we open it up at the end. But if you do have any questions, then do comment them now. That's fine. And I'll just scroll back up and read them at the end when we do the live chats part of the stream. Okay. So Joe wanted to know, what are the graphs of functions like sine of 2x, sine of 3x, or even x sine x? Okay, so we'll start with the first two, and then we will pop up to the third one, tricky one, x sine of x. Right, well, we're going to need a graph of sine of x. That's going to be our sort of starting point here. So I'm going to look at sine of x. I'm only going to consider x positive, just because it doesn't really matter. It will be reflected in the axis, but we'll just concentrate on x being positive for now. And think about what's happening. So sine looks like that. Right, let's get some different colors on the go. So let's use apparently I'm really into my pink chalk today. So let's go with my pink chalk for sine 2x. Now let's think about what this sort of means, right? When you're trying to plot sine, there are some key points that really help us out. So, right, for example, we know that sine is 1 at 90 degrees or pi by 2. I'll stick to degrees. This is because someone asked a question about radians. I'll stick to degrees. Right, so 90 degrees, because we use degrees in the lesson. So be consistent. And then we get to the point when it's 0 at 180 degrees. Then this is like 270. This is 360. Right. And obviously this is 0. So these are like the key points. You've got that sine of x is 1 at 90 degrees, right? So let's write that out. So sine of x is, so sine of 90 degrees even. Oh, wait, sine of x is 1 at x equals 90 degrees. So if I'm now trying to plot sine of 2x, right? So if I plot sine of 2x, then this will equal 1 when 2x is equal to 90 degrees. Right? Because sine of something, we want to try and solve sine of something equals 1. And we know that one point which satisfies that is sine of 90 equals 1. So here, this will be true at 2x equals 90, which is just x equals 45 degrees. So this is why it can be helpful to think about some of the points, like the peaks and the zeros. Because we're going to get the same thing happening at 180. So sine of x is 0 when x is 180. 0 at x is 180. So sine of 2x is 0 when 2x at 2x is 180. So when x is 90. And we could try this for a few other points. But what we're really seeing is you're kind of just sort of squashing everything a bit, is one way to think about it. So whilst here, for sine x, you have this sort of wave shape, this peak U shape happening between 0 and 180. When you go to 2x, your wave shape, it still has to go up to 1 at 45 degrees, but it's got to get to 0 at 90 from here. So it's kind of got to do that. So you're like squashing your wave a little bit. And then you're going to get the same thing down here. So by 180, you've got to be back at 0. So this comes down and goes like that. And then you get the same thing. It's got to go up and come back to 0 by 270. And then go down and come back to 0 there. So instead of having two bumps, the white one is sine x, which just has the one positive peak, one negative. When you have sine of 2x, you just kind of condense it, kind of like one of those French instruments, accordion, kind of like an accordion. You push the graph together a little bit, and you just get more bumps. And the accordion is actually quite a good picture to have in mind, because if we went a step further, let's use orange. We went a step further and looked at sine of 3x, exact same idea. So instead of 3x has to be 90 degrees, so x is 30 degrees now. So you're going to get your peak even sooner than we had. It's not going to go through 9, it's going to go through 60. Like that, and then you're going to have to, let me think about this now, come down, go back up, and then come up. And at 180 degrees, I need to be at 0, don't I? So it's even more squashed when you do sine of 3x. We've now got, this one's going to come down, come back through there, through there, through there. Right. Okay. So we went from 2 peaks to 4 peaks, and now we've got 6 peaks, right? So here we had 6 for sine of 3x, and we had 4 for here, right? Where the peaks are the max and the min, right? Each one I'm calling like a peak or a hump. And then you also had, and you only had 2 for that. So as you increase the value of your x, so you go through, you could sort of write it as sine of kx. And as you increase k, you're just squashing the sine curve more and more this way to get more and more peaks. So it's you're starting with your big wide accordion with only 2 like peaks, 2 kind of bends, and then you're squashing it in, so now it has 4, and then again, and it has 6. You're kind of squashing it together to create more and more waves, more intense waves. It's one way to think about it. So that's sine of 2x, sine of 3x, and we could do this for any k. We just squash the graph more and more over towards the y-axis. Now, if we want to think about x sine of x, that's a whole other thing. So let's have a little go at that one. Let's rub this off. So now the idea of this, there are 2 ways to think about this. The way I like to think about it is we've still got sine of x. So you could try plugging in some values of x into this, for example. So if you plug in x equals 0, right, you're here. If you plugged in, so if you wanted to plug in 90 degrees, which would be in radians, you'd have to kind of work in radians here. You would plug in, pi over 2. So then you'd get pi over 2 times sine of pi over 2, which is 1. So you'd get pi over 2, for example. So you can work out various points if you really want. But I don't think that's necessarily that constructive. It gives you a bit of a feeling for what was going on. Now, what's going to happen is, or one way I like to think about it, is the sine, you're still going to get that wavy behavior, right? Because we saw from our sine graph, it goes up and down. It has this periodicity, and it creates these waves. And so you're still going to get the oscillations from sine of x, because you're multiplying by something positive. So again, if I just consider x being positive, I've got a positive number multiplied by something that waves between -1 and 1. So I'm still going to get something that wiggles. But the size of the thing that wiggles is controlled by x. So if I were to plot y equals x here, like so, and also, in fact, y equals -x, when I have small x, right, this is something small times sine of whatever the number is. So the actual size of my sine function is determined by x. So we know that sine of x, rather than writing like that, we know that sine of x belongs to -1, 1. It's always between -1 and 1. And so as it sort of oscillates, the actual size of the whole function is determined by x. So these lines are actually the boundary of your sine function. So for small x, it's small, and then you're going to get your oscillations like this, where they go between the y equals x and -x lines. So you can plot this yourselves, you can try some points, and it will look like this. But the key thing is this idea that the sine function tells you it's got to wiggle about, has to do that. And then it's the x at the front that provides these like boundary curves that it can't go beyond. So you end up with something like this, and this will get bigger and bigger and bigger and bigger as you continue to increase x. So it's a really nice question, actually, Joe. So thank you. And that leads me really nicely into the next question. It's almost as though I plan these. Well, I plan the order, I don't plan the questions. The next question, which came in from Owen, and Owen asked about sine x divided by x. So this is a classic question, but one that I'm more than happy to have a go at here. So Owen wanted to know what happens to sine x divided by x as x tends to 0. So Owen's question, sine x divided by x as x tends to 0. Right. Few different ways of thinking about this. And because we've just been talking about graphs, I'm going to start thinking about graphs. Okay? So if we call this is my y. So what you could do based on the discussion that we just had, so I said that when you had x times sine of x, you still get the wiggly behavior, but it's bounded by y equals x and y equals minus x, those two straight lines. So now we've just got 1 over x times sine of x. So our boundary is going to be given by 1 over x, is a way to interpret the question. So before it was given by x, but now if we plot 1 over x, it's going to look something like this. And if we plot minus 1 over x, it's going to look something like that. Right, so these two, and we'll do them in a different color and label them so we can make sure everyone's following what we're doing. So these curves are y equals 1 over x, and y is minus 1 over x, right? So this is just what we did last time. We had y equals x and y equals minus x as our two boundaries because we had x sine of x. Now we've got 1 over x times sine of x. So our boundaries are going to be given by this 1 over x function. So in between here, this is the easy bit. As we get really small, right, this just has to get small. And then it's going to get a bit bigger. And now it gets tricky. So this will go to 0, right? And this will get bounded and will be very, very small. So you've got like waves which are decaying. So you can think of it as your sine function, but the amplitude gets smaller and smaller and smaller. So it's like if you created waves on like the surface of a pond or a lake, right? They're really big near where you make the waves, and then their amplitude decays as you move further away. So that's like what's happening here. Now the tricky bit is what happens near 0, and this is exactly why I'm guessing Owen asked this question, right? Because on one hand, if this was just the boundary, then there could be possible that this thing just continues to get bigger and bigger and goes all the way to infinity. Maybe. That would be a perfectly reasonable thing to sort of think about, right? So it's not a proof, and it's actually incorrect, but it would follow this idea of having our sine function bounded by these two curves. So the problem here is we have to be careful because we are dividing by 0. So in our other function, when we had y equals x sine of x, this was fine when we took the limit as x went to 0 because we just got 0 times sine of 0, which is 0 times 0, which is 0. So that just all kind of worked, right, with no problems. But here, we're going to be dividing by 0. And as we have seen, in fact, with cot and with tan, that can cause things to go to infinity. Sometimes it doesn't. It's like a difficult thing to deal with, especially because we've got 0 divided by 0 in this situation. So that means you've actually got to take the proper limit. You can't just substitute in 0 and say it's infinity or 1 or whatever. You actually have to take a limit because we've got 0 on top, 0 on the bottom. And that can actually be equal to anything, depending on how you take the limit. So we do have to be very, very careful. So in order to do this, there are a few different ways to do this. I think my favorite way is probably using power series. And I do want to talk about power series, but before I get to using power series, I also want to, as my final question of the day, touch on a question that came in from VJ, which was about hyperbolic functions. So I'm going to kind of take a slight detour, take like a screenshot, picture this in your mind. We're going to work out what is the limit of this as x goes to infinity. But in order to do it, I want to show you how to do it using power series. So we're going to take a little detour, talk about power series and some other functions, and then come back and get the answer. Okay, so I hope that's all right. I just want to try and cover everyone's questions all at once. And it should make the limiting process make more sense, I think. So I'll leave this one on, but I'll get rid of the graph. So we know what the graph looks like apart from near zero. That's the only bit that we're struggling with, which is why Owen's question is so important. So the reason I wanted to talk about power series, and this links nicely with Vijay's question, because Vijay asked about hyperbolic functions. So I don't know if any of you, I'm sure some of you will have heard of these. So we have these things called cosh of x and shine, or sinh. Some people call it sinh, some people call it shine. I'm very much on the shine side of things. I think it's a nicer thing to say. Sinh, just don't like it as a word. So these are hyperbolic functions. And these are very similar to cos and sine, which is why they have the same, right? It's why it's cos, why it's sine. But then they have a h, which means it's the hyperbolic version. And they have formulas. So cosh of x is e to the x plus e to the minus x divided by 2, which is just the exponential function. And shine of x is e to the x minus e to the minus x divided by 2. Right, so they're just the formulas for our hyperbolic functions, right? So that's just how we define them. You plug in the numbers, plug in the value of x, you can calculate your exponentials, you can calculate cosh and shine. Now, the interesting thing is how they relate to cos and sine, and that was Vijay's question. How do the hyperbolic functions relate to trigonometric functions? So what we can actually do is write cos of x in terms of exponentials. So cos of x, wait, actually, I tell you what, rather than me jumping in there, let's use Euler's identity. Because I was asked about Euler's identity by somebody called Tom, great name, asked me about Euler's, well, rather than, let's say, Euler's identity is maybe a bit confusing because Euler's identity usually means e to the I pi plus 1 is 0, the one I have tattooed here, in fact. But we want to think about Euler's, maybe let's call it Euler's theorem. There are many Euler's theorems, but we want to think about Euler's theorem here, which tells us that e to the I theta is equal to cos theta plus I sine theta. Okay, so we're going to assume that is true, right? Because we have to start somewhere. So if you've seen this before, great. If you haven't, don't worry. I'm telling you this is true. E to the I theta is cos theta plus I sine theta. So if you assume that's true, what we can now do is we can rearrange to express cos in terms of exponentials. So if this is e to the I theta, then e to the minus I theta is by definition cos of minus theta plus I sine of minus theta. Right, so I'm just replacing theta here by minus theta. That's all I've done. But we know that cos is an even function. So cos of x is equal to cos of minus x. So this is actually just cos of theta. So we can rub that out. And sine is an odd function. So sine of x is equal to minus sine of minus x. So we can therefore put a minus there and get rid of that one. So e to the minus I theta, using the fact cos is even, sine is odd, gives us cos theta minus I sine theta. Now we can just add them together, because if I do the top one plus, if I do e to the I theta plus e to the minus I theta, the sine terms cancel. They completely vanish. I've got plus I sine theta minus I sine theta. So they will just cancel when I add them together, and I get two lots of cos. So cos of, let's write it as x, is actually just e to the I x plus e to the minus ix over 2, just by adding these two equations together. And then if you do the top one minus the bottom one, we then get 2 lots of sine. So this one minus this one, causes cancel, and I've got 2i sine theta. So therefore, sine is the top one minus the bottom one divided by 2i. Okay, so start from Euler's theorem, consider it for minus theta, using cos being even, sine being odd. Combine them, add them together, and rearrange for cos. Subtract them, rearrange for sine. And it's important that the sine one has got an I on the denominator. It's an important thing to remember. Now, those two formulas for cos and sine over here look very similar to the formulas I've got for my hyperbolic functions over here. Very, very similar. Can anyone tell me how do we make one of them equal to the other? This is where you guys, you're a good like 40 minutes into the live stream, so I think it's about time I asked you a difficult question. So I want to know, what is the way to write cosh in terms of cos or sine in terms of sine? So have a little think. You've got all the information you need in those two boxes. And I will just rub off this. I would recommend starting from cos, was how I did it. You can do it in different ways, but I started with cos and just replaced x with something else. Multiply sine by I and x becomes minus ix, that is sine. Yes, good, Joshua. Right, you're on the right track. That might even be correct. It's difficult, obviously, I'm aware it's difficult to type maths in your YouTube live chat box. Well done. So there are different ways to think about it, but what I'm going to do is start with cos and then say, if I consider cos of ix, and then just use my formula. So cos of ix is equal to e of I times the thing in the cos. So that's going to give me e to the I squared x plus e to the minus I squared x over 2. But I squared is, of course, yes, exactly as Joshua said, I squared is, of course, minus 1. So this is minus, and that becomes a plus. So that is just cosh. So that's the relationship between the hyperbolic cosine, cosh of x, and cos. You simply have cos of ix is cosh. So they're very, very closely related functions, believe it or not. And then you do a similar thing for sine. Sine's actually a little bit trickier. So sine, oh, actually, so what you do, I think this is what Joshua said actually, is you do minus I times sine of ix. So we have to multiply by the I to get rid of the denominator. We have to do that. So we're going to get minus I. So then we've got the i's on the bottom disappeared. We've still got the half. And then we need sine of ix. So that's going to be e to the minus x minus e to the x. And then we also had a minus sign, didn't we? So minus plus. And that is exactly what sine is equal to. We've got the plus with the e to the plus, minus e to the minus, plus on the e to the x, minus on e to the minus x. So we get that relationship. So cos of ix is cosh, and minus I sine of ix is sine. Okay, so that's the answer to VJ's question about hyperbolic functions and their relation to trig functions. Now what we're going to do, very, very final thing, we want to answer Joe's question. What's the limit of sine x over x as x tends to 0? So we don't need these anymore. But the reason I wanted to talk about the hyperbolic functions is because now it allowed me to introduce these two formulas for cos and sine. So I can get rid of this one. So we now have two formulas for cos and sine. And we're going to concentrate on the sine one because we're trying to work out sine of x over x. So I can work out the infinite series or the power series for sine using this formula because I know the infinite series for x, for the exponential function, sorry. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. That is the power series of an exponential. So if I combine these exponentials down here, that means that sine of x is 1 over 2i times e to the ix. So that's going to be, if I write it out properly, ix to the n over n factorial plus the sum minus ix to the n over n factorial. Right, so it's a pretty complicated expression. There's two infinite sums in here, from 0 to infinity. But the important thing is, this version of sine, and then using our exponential power series, combining them in this way, you can actually expand out some of these brackets, because we know that when I is taken, I squared gives you -1, I to the power 4 gives you 1, I to the power 3 gives you -I. So you actually get a repeating pattern of sometimes with i's, sometimes without, sort of in all of these terms. And when you do this, you multiply out these terms and kind of add them together, the magic happens. Because when you do that, most of them cancel, and the whole thing turns into x minus x cubed over 3 factorial plus x to the 5 factorial plus dot, 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 forever. So what you end up with is your sine power series. So I highly recommend that you actually expand out a few of these terms. Just do, n equals 1, 2, and 3 for each of them, and convince yourself that the right terms cancel and you get just the odd powers. So what you end up with is that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And you just carry on. So it's all the odd powers of x divided by that number factorial. And you swap signs. The signs alternate from plus to minus. Now, how does this help us with y? This, remember, was ultimately what we were trying to do. We've gone through this whole power series derivation so we can calculate this limit. Because now, if I calculate sine x over x using the power series here, it's just 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial plus, well, minus. But then you just carry on with the pattern. So now, finally, we can take our limit because we have no x terms left on the denominator. So we can just now take the limit as x goes to 0 of y. So 1 stays as 1. This term now goes to 0 because it's 0 divided by 6. So it's 0. This term is 0 divided by 120. It's 0. All the other terms have a power of x, positive power of x in them. So they all go to 0. So your answer is just 1. And so on our graph, to come full circle, the graph of sine x to the power x, sorry, sine x over x, it starts at 1, and then it starts to decay and goes really flat. So something like that. is what it looks like. Right, I'm aware I went quite fast through that last question, but I did want to leave at least some time open to questions from the live chat. So I'll give you a minute or two to collect your thoughts. I'm going to clean the board, and then any questions at all, if they're to do with trig, that's great, or if they're to do with power series, I'm sure you probably have questions about some of the stuff I wrote on the board. But if you have any other maths questions, throw them out there as well, and I'll pick some to answer for the next 10 or so minutes. And also remember, because I went through that quite quick, remember you can always come back and watch this whole video again tomorrow. So YouTube takes a while to process it, but I think it will definitely be available tomorrow, like lunchtime, within 24 hours. So if you want to come back, you can rewatch everything we just did, right? And maybe pause it and make sure you're able to follow what we did. But I will give a summary. I see somebody has asked for a summary, so let's do that. Right then. So what did we do? We started, I think the key bits were the power series, weren't they? So key things to remember then were we started by me telling you Euler's identity, right? So we had Euler's identity was sine, sine is it? Cos of x plus I sine of x. So we started by assuming this. Then we said using this formula, we could calculate e to the minus ix using the fact that cos was even, sine was odd. We could calculate that this was cos of x minus I sine of x. And then those two results together allowed us to deduce that cos of x was given by e to the ix plus e to the minus ix over 2, and sine x was equal to minus ix, e to the plus ix minus e to the minus ix over 2i. So we started with Euler. This came from odd and even functions. These came from algebra, adding the 2 and then subtracting the 2. Then we said, well, I know that the e to the x has a power series from 0 to infinity of x to the n over n factorial. And if I were to write out the first few terms, you get 1 plus x squared over 2 plus x cubed over 3 factorial plus, right? That's your exponential function. So using this definition, we can plug this in for sine, and it turns out that sine of x is equal to the odd powers only. And cos of x, which I didn't do, but you could calculate in the same way, use our formula, plug in ix into the exponential formula. Cos of x is all of the even powers. Yeah, so 1 minus x squared over 2 plus the 4 factorial plus. So you also get your cos power series. Again, alternating signs, plus minus, plus minus, plus minus. And then having these power series definitions for cos and sine, so this definition and this one, these are now really helpful when you need to calculate limits. So the final step was to just divide this whole thing by x, and then we could actually just plug in x equals 0, and we got our final answer of 1 for that limit. So that's a nice, neat summary of the power series for cos and sine. So it came from Euler's identity here. Remember this is Euler. And it came from the exponential function. Like our two key things. Those two key things allowed us to do everything else with cos and sine. Right. What else have you got for me, people? Let's have a read. There are quite a few questions here. Okay. I think the question, so that was a very good question about radians and degrees. We use radians because degrees have like, they don't really have an arbitrary, it's like an arbitrary unit that you just don't want to have to deal with. So converting it to radians allows you to think of things in terms of circles, and they don't have units. So it's much easier. Like you saw when I was trying to draw my graph, I didn't feel right to say sine of 90 was 1. While sine of 90 degrees is 1, the actual value in radians is sine of pi over 2 is equal to 1. So when you tried to do something like x times sine of 90 degrees, x being 90 degrees makes no sense. But x being pi over 2 makes complete sense. So it's kind of, yeah, it's just a better notation, I think, and allows you to actually think about functions rather than just sine and cos in terms of triangles. All right, what else have we got? I've got some love from Mexico. Thank you, Rodrigo. Okay. I have 2 points A and B on a plane at a distance between them 1 meter and drove them to a point C when the angle formed is how to find. All right, I guess we'll do that question, Muskan. Let's have a go. I have to draw a diagram and write it out. So get rid of my summary. This looks like a almost like a straight line graphs combined with trigonometry question. So could indeed be a good one. Let's see. Oh, I should also add, everything I just went through is so far beyond high school maths, it's ridiculous. So there are already people watching who got lost. Like, honestly, don't worry. This is definitely like early university level stuff for sure. Talking about infinite power series and different things. But, you know, I think it's quite fun to challenge ourselves. Right, so Muskan, your question is, I've got 2 points A and B, and the distance between them is 1 meter. Right. A to B, 1 meter. Okay. Joining them to this sounds like a homework question, by the way. If this is your homework, this is a very cheeky, very, very cheeky request, but I've started now. Joining them to a point C when the angles formed at point A are 60 degrees. All right, so this is 60 degrees. Okay, and the angle formed at B is 75 degrees. So it's a triangle. Fabulous. This is very relevant to trigonometry. And this is 75 degrees. Okay, and we don't need units, so we can just call that 1 instead of just 1 meter. Right, and you want to know the distance from the middle of A and B to C. So you want to know the middle of A and B to C. So it's not necessarily a right-angled triangle then, is it? That's a bad picture. Okay. Right, I think I get the idea. Okay, mine looks like a right-angled triangle. It's not necessarily going to be a right-angled triangle, is it? Right then, let's think about this. And you want to know, so rather than that being 1, this is actually a half and a half. But I don't know the angle in the middle. So this is my interpretation of the question. If I've interpreted your question wrong, Muskan, I apologize, but we're going to solve this one. Right, so I've got ABC. Oops, let's do capitals. Normally for points, and I've got half and I've got 60 degrees. Right, and I want to know that length there, but I don't necessarily know. Maybe we're going to use the sine rule, you know. Maybe we're going to go back to question 1 and use the sine rule. So I've got, so if I draw this triangle, let's call this number 1. If I draw triangle 1, what have I got? I've got some unknown length here. Then I've got a 60-degree angle. And then I'll try and draw it so it's not obviously a... So the point is this is not necessarily a right angle. We don't know that. So that's a half. This is A, and this is 60 degrees. And I want to know x, but it's not a right angled triangle. See, if this was a right angled triangle, then we just use trigonometry and we're done. Really easy. But it isn't, unfortunately. So it's going to make this a bit trickier. So what I would be tempted to do is, let's think about this. So let's call this angle here y. So now my sine law tells me that sine of 60 over x is equal to sine of y over a half. Okay, so I don't know the angle y, and I don't know x, but I know that the sine of this angle over this length is equal to sine of this angle over this length. Now I can do the same on the other side, I think, and get something else. So the triangle on the other side, let's say it looks like this, where this is 75 degrees, this is a half, this is still x, and this is some other unknown length, let's call it z, and then the angle opposite, let's call that alpha. Right, so sine law here tells me sine of 75. Oh wait, why have I done that? I didn't need to know. Nope, don't need to know that. Ignore me and ignore that. That's z. So sine of 75 over x is equal to sine of z over a half. Right. So where can I go from here? So I think we've got two equations, but we've got three unknowns. We don't know x, we don't know y, and we don't know z. So what could we really do here then? We need one more equation involving x, y, and z, right? So my approach here is to try and construct simultaneous equations. So whilst we don't actually care about the values of y and z, the key thing is, oh, I know what the third equation is. Yes, okay, I've done it. You can see how much I enjoy solving problems. Right, so we don't care about y and z, we only care about x. But to construct true equations, we have to label the other angles y and z. Now, the thing that I know is this is a triangle. ABC is a triangle, right? So I know that 60 plus 75 plus the angle at the top must equal 180. Now, the angle at the top, based on my pictures, is y plus z, right? Because y was the one up here, this is y, and this half of it is z. Part of it is z. So I know that this is 135, so 45. So I know that the final equation is y plus z is 45 degrees. So I'm not going to do the algebra because I don't have a calculator. Equation 1. Equation 2. Equation 3. Solve those simultaneously. It's got three simultaneous equations. Plug the numbers in a calculator for sine 60, sine 75. Solve it, and you'll get x and y and z as well. Right, perfect. Good question, Ms. Khan, actually. I still think it sounds like your homework, but fair enough. You've now got an answer to your homework question. Right, so I've actually gone 6 minutes over. I got so into that. So thank you again, everyone, for joining me. This is the penultimate one of these, isn't it? This is the fifth, so the second to last. So next Friday, 4 p.m. UK time, same time as it's always been, will be the final Tom Rock's Maths Appeal live stream. The topic next week is probability trees. So basically, we can spend an hour talking about probability. So if you've got any problems to do with probability, if you enjoy probability, you're studying it, you don't like it, you're stuck, whatever, I'll be doing a live stream in exactly 1 week for an hour on probability. So again, like before, if you send your questions in early, then I will definitely go through them, because I always start by going through questions I've been sent before, and then at the end, I'll open it up to the live chat exactly as I've done the last few weeks. Okay, so I think that was pretty good. I quite enjoyed that one. I hope you all did too. And hopefully I'll see you all in a week. And remember to watch the new Maths Appeal video on Monday. Monday, it will be out on probability. Right. See you all soon. Bye-bye.